So, chapter 14 in the Lamley book, IPv6. IPv6 is something that's imminent, going to become imminent ever since I've been doing IT, which is getting close to 20 years now. Something that's we're going to have, and we are eventually going to have it, but we've done all of these things, workarounds for IPv4, all the things that you didn't really like to do in an IPv4. We use NAT, that saves addresses. We use proxy servers, which is not the topic of CCNA, but a proxy server is a device, a server that you go to and it goes to the internet, so you really only need one IP address for a whole bunch of users. We've done subnetting and variable length subnet masks. I know we didn't really talk about those yet. Variable length subnet mask just means that when we did subnetting before everything was the same size network, variable length, you can have different lengths of subnets in there. So, and they say to overcome the IPv4 shortage, there are about, roughly speaking, 4 million IPv4 addresses in the address range, which is fewer addresses than there are people in the world. And then you have all the other things that are coming online, the phones, tablets, people with multiple computers. So we need to, and really do have to, expand the address space. And with IPv6, which uses a 128-bit address space, there are, you see the number there, 3.4 times 10 to the 38th addresses, which is, the people's different things. They say it's as numerous as there are grains of sand, and somebody else said that that leaves multiple, probably a million IP addresses for every square centimeter of Earth. So will we run out? Not in my lifetime. Probably not in your lifetime. And probably not in our kids' lifetime. That's a lot of addresses. But we're adding a lot of devices, and I think we talked about that early on. People putting a refrigerator on the internet. Put cameras on the internet. Everybody's got a cell phone now. Even I've got a cell phone.
Yeah, but you're usually replenishing a lot too. You get rid of an old phone, you get a new phone.
Yeah, but we're still adding them worldwide. Yeah. And this is, you got to think about this as a worldwide situation. So that means, which means you got to bring China into the mix, and with the number of people there that are getting phones and computers, and cars have IP addresses, and maybe multiple IP addresses.
Yeah, I have.
You get on the internet on your car. So, IPv6 advantages and disadvantages. I guess the disadvantages, we've got to learn a little bit about it. The advantages, it does an awful lot of stuff for you automatically, what you're going to see in the labs. The addresses are a pain to type. The demo lab, I already put in the addresses and the routes, the static routes, because you have no idea how long it took me to do that with the typos that I make. But what I did learn is that copy and paste, because you can, if it's something that's very similar in the simulator, copy it from someplace else, paste it in, and go back and make your changes, so that you don't have to do all that typing. It really does. It's hexadecimal, 128 bits, uses 4 hex numbers. We'll look at that per segment, which means that we've got, what, 16 of those. So generally it's going to use a 64-bit network address. There are network addresses. We don't have subnet because we have 3.4 times 10 to the 38th addresses. It's not well supported in the U.S. It is in some other parts of the world. I think that, and I may have mentioned it, but at one time, and I don't know when that was, these are all things that you read as you go through these classes, they had one Class C subnet, 254 hosts, allocated for the continent of Africa. So addressing becomes a situation. As far as I can tell, all of the IPv4 addresses that IANA, who is the numbers people, controls, have been issued. That doesn't mean that all the addresses are used. I was doing a class, watching a video or something from one of the CCNA guys. He said he was at a conference at the University of Iowa, I guess, and he said that somebody there said, we got 2 or 3 Class B subnets. That's a lot of addresses, 65,000 whatever addresses there. So there are some people, companies that got at the front end of the internet, IBM, MIT, the Stanford, the people that were in the original DARPANET, some of those wound up with Class A networks. And Class A networks got, what, 16 million addresses in it. So I'm sure some of those are still floating around, but there aren't any left to officially give out to people. So we have those things. The IP addressing expression, which is written in hexadecimal 1, 2, 3, 4, 5, 6, 7, 8 sets of 4 hexadecimal bits. So each of these is 4 bits, and 4 bits is actually a nibble. And he uses that term sometimes in the book. What we used to always say, but that used to be something they really wanted you to know, but 4 bits, 8 bits is a byte, 4 bits is a nibble. And I forgot what 2 bits. 2 bits also has this thing. So we have 1, 2, 8, 16 of these. We have 8 16s is going to give us 128 bits. 128-bit address space. And what they talk about here, global prefix. The global prefix is going to tell you what kind of address it is. Whether it's, they call it, and we'll go through some of the names. Link local, which is basically what the PIPA, the 169 addresses are. Local, they use 2 terms. Local used to be called site. They have not definitely settled on all the terminology either. It changes some. And then we have universal, multicast. The last slide or last bullet in that previous slide. There is no broadcast in IPv6. There is a multicast, and there's a thing called an Unicast. Unicast allows you to have the same address on multiple devices, and Unicast will go to whichever one's the closest routing-wise when we do those things. But typically, and then we talk about subnet here. And I've seen a couple of these, they talk about the prefix and then the ISP, and after the ISP, the subnet. What this does for us, the way it's set up, and it's set up hierarchically, is it automatically aggregates the addresses. We talked about supernetting as aggregation, and I kind of gave you guys the example of a place where I used to work. We were the 10.60.x.x. So in our network, we had maybe 10.60.10, 20.30, and so on. So we had a router that routed within the network. From outside the network, from the headquarters activity, and everything went through the headquarters activity, they would set their route up to just go send everything that started with 10.60 to us. And that's what route aggregation is. This thing is built hierarchical so that the ISP will get addresses that they don't have to have multiple entries into the routing tables with. What it really does is simplifies the routing table, simplifies the work that the routers have to do. 32 binary bit, or 128 binary bits, 32 hexadecimal digits, grouped in 4-digit hexadecimal groups, and they're separated by a colon. And if you are going to go to a website in IPv6, you gotta enclose the IPv6 address in brackets because the HTTP already has a colon in it. So you have to separate them that way. Here's another, this is maybe a better image of the structure, 32 bits, the ISP 32 bits, and going to the customer site, 48 bits, and then another 16 bits here for the subnet. And I saw a thing today that said sites are really geographic locations. Like maybe California, New York, Southeast, things like that. And if you look at what the providers do, they kind of do that. They aggregate their addresses. But in any case, generally we're going to have 64 bits left for the interface ID. Where before the maximum number of bits that we could have had for the interface ID was 16. Remember, in binary, every time you add one binary bit, you double it. Because whenever we go back 2, 4, 8, 16, 32, if we add 1, 64, and on down the line. The shortened expression, some of these are going to be in the book, and some of them I took from other places. The full address is written like 2001, and 2001 is an address that's not routable. It's one that said that's used for like demonstration for like we're going to do in the labs. You shouldn't see them as routed. So we have this address 2001, 0 DB8 3C4D 0012 000 000 1 2 3 4 5 6 AB. That's a lot to type. To help a little bit, leading zeros don't have to be typed. And they did down here, they did them anyway. They wouldn't have had to type those. So we really don't need to put these leading zeros in. Any of the leading zeros in. If we have a series of zeros, they can be replaced with a double colon. So it helps a little bit. No leading zeros. A whole bunch of them, like the broadcast, or excuse me, the loopback address 127.0.0.1 is a whole bunch of zeros and 1, which is just written as : 1. So you don't have to write. If you have, it doesn't matter how many of these there are, you can use it, but you can only use it one time. So you can use the : once. That's because if you used it more than once, it wouldn't have any idea where these things are. It knows how many bits are supposed to be there. It knows about the leading zeros, takes them out. That's all okay. So in this one, okay, they're just doing a little bit at a time. 2001, all these zeros, again, the zero sequence by the : the leading zeros we can take out. Got that in the wrong place, to the 12. If we have other groups of zeros like this, we just write the digit 0. Then 1, 2, 3, 4, 5, 6, AB. Helps a little bit when you're trying to write these things. Because, like I said, they are kind of a pain. So, the types of addresses that we have in here. Unicast is computer to computer, device to device. A global unicast address, and they're going to start with 2000, are routable addresses. The link local addresses will start with FE0, and if you look at your Windows machine, if you do an ipconfig/all, as long as you haven't disabled IPv6, you'll find an FE80 address in there. So these are link local addresses. They're like the APIPA. And if you remember, APIPA addresses are those that if you are configured to get an automatic address, a DHCP address, and you can't find a DHCP server, Windows will give itself a 169.254 address. Unique local addresses are in fact local FC00 is what they start with, and they're similar to the private IP addresses, the 192, 168, the 10s, and the 172.16s. Multicast, which it uses a lot, starts with FF0. And then we have this Anycast, which is thrown in, and the Anycast is used whenever we put a multiple or the same address on multiple devices. The Anycast then finds the closest device with that. And if you think about it, if you go to Google and do a lookup, it comes back pretty darn quick. You think the whole world is doing that? is going to the same Google server? They're not using IPv6 because you guys probably have AT&T, and I don't know if they do or not. I did a check. There's a website you can check. Time Warner doesn't, in this area at least, doesn't support IPv6. So what they use, and it's a DNS trick to do that, that you have a name resolved and it will resolve to the closest server. So with this thing, will go to the closest device routing wise. This is the loopback we talked about. All these zeros, even with the shortening with the other one, all this is the 127.0.0.1 can be written as : :1 because we have a string of zeros here. Regardless of how long it is, we can do consecutive zeros as a : This is more of the trying to give an image of what goes on with these addresses. The registries are in different parts of the world. We have one in Asia, one in Africa, and I've forgotten the abbreviations for them, one in Europe, North America. So the registry gets a set of addresses which are going to be hierarchical so that they can be easily aggregated. And then we have the ISP prefix. We go over here to the 32 bits. The site prefix takes it over to 48 bits, and site prefix is a geographical, not necessarily Charlotte, although when you started doing those, you would try to break it out. We had a group of addresses in Charlotte, a group of addresses in Atlanta, a group of addresses in Nashville. And then we have everybody's subnet. But when we write the addresses, whatever it is, we're going to write it /64. This just means that you in the subnet get to control the digits that go in here, the bits that go in here. And you really don't have to type a lot of addresses to make this thing work, because the routers, and one of the labs is to set up auto configuration. The routers can actually give, once it knows what network it's on, the router can give the workstations IP addresses, which simplifies things a little bit. Problem is, it's not a full DHCP. So these are some of the addresses, and these I think are right out of the book, the table, right? All the zeros here is the equivalent to IPv4's all zeros, and this is typically the source address before it receives an IP address. So when we do the DHCP discover a message, the IP address that goes in is all zeros. It's going to be the same thing here. Although there is a DHCP for IPv6, DHCP6, but Cisco doesn't support it extremely well. All the zeros and the 1 is the : :1, which is the 127.0.0.1. If you use how an IPv4 address would be written in an IPv4 IPv6 environment, you lead it with zeros and then use the IPv4 address. The 2000 : and that means 2000 and anything after it. It's the global unicast range. The FC0 is unique local unicast, and that is like the private IP address range. FE80 is link local, is like the APIPA, and these are the best that I could come up with. FF0, the multicast range. These reserved for examples and documentation. In the 2001, and the DB8, which is the address range that he uses for all of his labs, is reserved for examples and documentation. They shouldn't be routed. The routed ones should be up here with the 2000. And 2002 is used for 6-to-4 tunneling. What happens if we need 6-to-4 tunneling if we have, and we'll have these really big network. So we had a company that we had an IPv6 network and an IPv6 network in two different physical locations. And then in between it, well, this is my cloud, we have the internet, which uses 4. What we use is 6 to 4 tunneling. What we really do is take the 6 packet, and this is a really great 6 packet, put a 4 header on it so it can go across the internet. When it gets to the other end, the IPv4 header gets stripped off, and then it gets to use IPv6 at the new location. So there's a lot of tunneling that goes on. Dual stack is the other way, and that's kind of what you get in Windows machines now, because generally you're going to have an IPv4 address. My router uses IPv4 addresses. The machine itself, I get the FE80 address, which again is the link local unicast address on it. If at home, if I ping a computer by name, it'll use IPv6. You can ping the IPv6 addresses, but it can use the FE80 on an individual segment. Just like you could use a 169 address. If we had everybody hooked up in here and everybody got a 169 address, we could use this. You couldn't get out of the room, or we're going to go through a router on them. It's the same way here. They shouldn't be routed, but they can be used locally. So we're going to use tunneling to do these things. And another one that I looked at says IPv4 is going to be around for a while. It's going to take a while to transition. As he said, you can't just shut down the internet for a week and say, okay, internet shut down while we upgrade our servers. Plus, you got to get everybody to upgrade their servers and their routers at the same time. Probably not going to happen. So it's going to be an incremental process. Tunneling is one of the things that's going to be around for a while. There are several different types of tunneling, but generally speaking, that's the way we would use these things. One of the things that you have to do when you start up the routers, they support IPv6, but it's not active. So you have to turn it on in the regular in just config mode with the command IPv6 Unicast Routing. If you don't do that, it ain't going to route. When you configure an interface, IPv6 address, so you notice that the commands that we usually just type, many, probably even most of them, we have to prefix with IPv6 so that the router knows that you're using IPv6 and not IPv4. Like most things, it'll help you out if you do that. But IPv6 address, the whole schmear here, but instead of writing 255 or FF 16 times /64, which says that 16 bits, that this bunch here is going to be the network address, and these, hopefully I got 4 left. Hopefully I got 4 left. 1, 2, yeah. These 4 here are going to be the unique node address. So we do have network addresses. We specify them with a subnet mask, but instead of writing the mask, we write the CIDR notation, /64/32. Most of these things are going to be 64. The other way I'm going to talk about this EUI64 address is we IPv6 address, and you notice here, 1, 2, 3, 4. I went too far here, didn't I? 1, 2, 3, 4, yeah. I messed up. There's the host, and you let me. And there's the network. We write the network address :/64 EUI-64, and it'll automatically construct an IPv6 address. So you don't have to type it in. The other thing, and you will have to do this even though he implies that you don't, on the interface to make the automatic configurations work, is type IPv6 enable. Theoretically, when you put an IPv6 address on it, it should enable it. It doesn't do that in Packet Tracer. So you'll have to use that command. And this is used to also to get the linked local addresses when we do these things. This EUI, Extended Unit Identifier, we have the OUI, right, the Organizationally Unique Identifier, and then I'll call it the serial number for the MAC address. And what we use in this EUI 64, we're going to use the MAC address to create an IP address, the host portion of the IP address. Should work because MAC addresses are unique, or at least theoretically they're unique. The problem is the MAC address is 48 bits. So what we do is split the MAC address in half, and this one is 000C, 42, 28, 79, 45. And in the middle, you add an FFFE. You just add those digits to it. And the 7th bit, 1, 2, 3, 4, 5, 6, 7, if we go here, that's the UL bit, universal or local. You flip the bit. If it's a 0, you make it a 1. If it's a 1, you make it a 0. The systems will construct those for you. And this thing, I did try it out at the house. You can take the little workstations in Packet Tracer, and the routers will actually give them an IPv6 address. And what it's going to give them is the EUI64 address. So, and that's just what it's called, EUI64. But that's the way it's constructed. Whether it be automatic or whether you manually construct it. If you manually construct it, obviously you've got to go find the MAC address, and then you've got to go figure out what the first 2 hex digits are, and change the second one, change the 7th bit. If it's a 0, make it a 1. If it's a 1, make it a 0. You flip the bit, invert the bit to do these things. And this is just another one down here is the 7th bit, universally local. Stateless auto configuration. If the MAC address, MAC address of interface is 00902716FD0F, insert the FFFE, and then we also the 00 to 2, 3, 4, 5, 6, 7, 8. So our 7th bit here is a 0, right? Because it's a 0 here. If we make that a 1, it puts a 2, because that's going on our 1, 2, 4, 8, 16, 32, 64, 128. The placeholders 1, 2, 4, 8, 16, 32, 64. Remember those? I know. They'll stay with you forever, even though you'll hate them, I'm sure. But we change it, we flip the bit, we make this a 2. So that the host portion becomes 0290227FF-FE16FD0F. So that is the way that you construct the EUI, and you can always recognize them because they're going to have this sequence, this hex sequence in the middle of the address. Auto configuration, the router needs the host prefix, the network address. So as long as it knows the network address, can send a router, and routers will configure other routers as long as they're communicating with each other. So if we had a bus, instead of draw a switch, a bunch of routers here, we can configure this one router with an address, then knows what network it's on. We can go over here and tell these guys to auto-configure. We don't have to put the address into it. So it does have some advantages. It does have some labor-saving properties.
So these computers are going to take over the world.
Well, they're kind of already doing that. When we're talking about cars that drive themselves, they're testing Uber, which is, they advertise, you use your car as a money-making machine. I see that out on television all the time. Pittsburgh has self-driving Uber cars, so your car's not a money-making machine in Pittsburgh, unless it's a self-driving one. Trucks, yeah, I think they've tried those out in Germany. I don't think they've actually put any on the highway here. They've got them on test courses, I know, but yeah. So, yeah, we kind of are taking over the world. But you know, you talk about that, and I'll digress a little bit. And the number of IT jobs have kind of increased. They've kind of stayed the same. When I first started, if you wanted to go put like Microsoft Office, if we wanted to put a Microsoft Office or upgrade it on all the computers in the building, 150 of them or whatever they were, if you wanted to do it here, you took your CD and you sat down at them and you double-clicked the executable and you installed it. Today, if I want to install Microsoft Office on 150 computers, I go to the server and create a policy, store the executable, the system locally. When the computer comes on, Office gets installed. Yep, it does it automatically. So, yeah, we're making progress. And what happens in the IT world, a lot of bad IT people out there, and you guys probably know that. They started out, they didn't stay up, didn't do things, didn't do courses, didn't do studying, didn't do reading. But it's the IT people that know how to make the system work for them are the ones that I think are going to succeed in this thing. But anyhow,
yeah, I want to read off the sheet.
That's what a lot of help desks do, as you know. And then if that doesn't work, I can't help you. Well, then they send it up to somebody that may know a little more and then keep going up until then. I had a friend that worked at Advance Auto, and when they get ready to make changes, they program all the changes. But before you can make a change on the system, you got to have a program to unmake the change in case it doesn't work. Because you shut down 10,000 auto parts stores or whatever they got, you're probably going to be in trouble. So to do the auto configuration, it sends a router solicitation message, and then the router answers with a router advertisement. And again, these you see down here, they're FF02, which we're in the multicast range, and one of them is a 1 and one of them is a 2. The IC into an ICMP message, and here it says ICMP type 133. Stateful auto configuration. Stateful means we got to do something. What we're really talking about here is DHCP. If you're going to do a DHCP 6 server, you're probably going to use like Microsoft or Linux to do that. Cisco has limited support for DHCP v6. I think it'll send a default gateway, maybe a DNS server, but that's about it. The IPv6 header, and here I put up the IPv4 header to see how complicated it was compared to the IPv6 header. The IPv6 header is bigger because it's a 128-bit address versus a 32-bit address, but it has fewer elements. And down here, the pink, orange, whatever color that is, fields, these fields are not in the IPv6 header. One of the reasons that you had to have this header link is because you had these options. Until you got here, it never knew how long the header was. The reason it needs to know how long the header is so that it knows where the data starts. So in the IPv6, we still have a version. This one over here is going to be 4, and this one over here will be 6. The traffic class, which is similar to the type of service. The type of service is used to prioritize traffic. And oh, by the way, I'll tell on myself, I did that on my router at home, and I found out by prioritizing my traffic, I actually cut my bandwidth on my router in about a third, because it was limiting certain applications, like Netflix. But we have the traffic class. The flow label here is to keep streams consistent. So it's used for different streams for these things. The payload length instead of the IHL, we have the payload length, which is how big the payload is. The next header here can be used to tell it which header it's going to be used next if it goes up the stack. It can also be used to tell it about one of the, it's not options, but one of the additions of these things, like ICMP could be in here. It could be telling it to use ICMP, for instance. The hop limit is like the old time to live. It's how many routers it can go through. And then the source and destination address, 128-bit addresses. And then that's what, as you can see, that's what really makes it much bigger than the IPv4. If we just look at the header, it really is much smaller. And it is a simpler header, which also means that it can be routed quicker once the routers are configured for IPv6. This is just something that I threw in just to see, just so you can see that ICMP still has messages: network unreachable, host unreachable, protocol unreachable, port unreachable, fragmentation needed. There shouldn't be any fragmentation in IPv6. What it actually does is uses one of these ICMP messages and goes from source to destination, goes through all of the routers, and goes through here. And if it gets one that says, hey, this packet's too big, I need to fragment, goes back, starts over, starts with a smaller packet size until it gets through, so that there shouldn't be any fragmentation at all in IPv6. So it actually checks the path, checks the maximum transmission unit, the MTU, that can be used throughout the entire path, so that it doesn't have to do any of that slowing down. Neighborhood discovery is something that's used to discover the neighbors. Instead of using ARP, we use neighborhood discovery, and this is a part of the IPv6. It determines the MAC addresses, and you can look in your Windows machine and it should tell you who all your neighbors are. It knows about them, makes information flow locally quicker. Uses router solicitation, router advertisements. We talked about those in the routers for auto configuration. Neighbor solicitation and neighbor advertisement are used in IPv6 also, multicast, in order to build this listing table so that it doesn't have to go through that ARP process every time. It does a duplicate ID detection or duplicate address detection, duplicate IP detection, which I always thought was kind of neat. There's DAD, which is what they call it.
I wonder why it didn't say replace ARP in the book.
Well, I know it doesn't. That's why I added it here.
Oh,
It doesn't exactly. There is no ARP, and this is the closest thing. This is the closest thing that you would get to ARP, is making the neighbor list, because that's what ARP did, right? It really made a neighbor list of everybody that's directly connected on the network, the MAC address listing. But it essentially replaces ARP because there is no ARP in IPv6. The neighbor discovery. These are the this is just showing again FF02 for all of these things. All routers respond. The router solicitation, and then the router advertisement for these things. The solicitation is basically asking for the information, and it gives it back. There's no broadcast. The multicast, a lot of things just have to get done once instead of multiple times. Broadcast applications that use broadcast are now going to use multicast. And the network neighbor discovery, here we have what is it? What the NS? Solicitation, thank you. You know what it's like. And then the announcement here, and it's the same thing. I need your MAC address. That's what ARP did, right? I need your MAC address, or it's the same thing. So it does a neighbor solicitation and a neighbor announcement in order to get that information, and it retains it. Static routing. I also, and I looked at the lab, and I think he does it, all of them, where you don't use the next hop address. The next hop address is really cool, except that when you do the auto configuration, it uses the MAC address, and then he's got an address typed in here that you're supposed to ping after you did auto configuration. Well, if your router's got the same MAC address as his router, unlikely, since they're supposed to be unique, that would work. So if he in the lab wants you to use a next hop address, use the interface, the outgoing interface. That will always work, because it'll send it out that interface regardless of what the next hop's supposed to be. But in the static route, again, we have IPv6 route instead of IP route. And then the whole schmear, the network address here. And we have, after the network portion, we have the : which means that it can be anything after that. : represents a string of zeros, and that's exactly what we would do if we were writing it as a network. And then the next hop address here, which again, if it's something that was auto-configured, you've got to go find out what that address is. The easiest thing, I think, is to just tell it which interface to go. It's both the same thing, and that's what the router really wants to know what to do, is which interface to send that packet out of. OSPF v3, we talked about OSPF, and when we did it with the IPv4 version, which is version 2, we went to router OSPF, and then whatever the process number was, and then the network that we were going to advertise whatever it was in an area 0. Right? In this one, you do IPv6 router OSPF, and then whatever the process was. And then you can use one for every router. It doesn't care what it is, because it is unique. Then you go to the interfaces. Well, actually a router ID. You do need to use a router ID, and you notice that the router ID uses the dotted quad format. The router ID is going to determine which router gets the information and provides it to everybody else. Instead of going up here and typing all the network addresses, you go to the interfaces, and the interfaces that you want to participate in OSPF, and type the IPv6 OSPF whatever 110 area 0 on those, instead of trying to list all the networks. In order to make, and this is maybe something that's specific to Packet Tracer, in order to make the auto configuration work on any of these things, putting the addresses, whatever else on them, I had to do the IPv6 to turn it on here. Enable. Yeah, once that happened, everything worked fine. So that's the overview of IPv6. Questions? I know you don't have to sub that. That's the good thing. What I want to do for the demo, the static routes in this thing are already configured, because I make so many typos and there's such a long list that you don't want to sit here and watch me type making mistakes. So I did that. And so that, let me get back to this guy, so that also that we didn't have to watch me configure all of the routers. I've already configured OSPF on the the LA and the San Francisco and the LA routers. Okay. So what I'm going to do is go down here to the corp router and see if I can make OSPF work. How's that? And the first thing we needed to do was IPv6 OSPF. Does that look right? No. What did I get wrong? You guys got to help?
How can you see them?
Yeah. IPv6 router. Yeah, I know it's a long way off. Isn't it? Router, no, it's because when we did OSPF, I just typed it, router OSPF. What you generally have to do is put IPv6 in front of these things, OSPF, and one's going to be the process number. And what it says is, pick a router ID, please, because since it doesn't have an IPv4 address, it can't automatically assign it an ID. So, and we'll do router ID, and let's do 8.8.8.8. It doesn't really matter. It doesn't matter what it is. So we have those things. Now we need to go to the interfaces, and I think that these are serials, right? Serial 000. I couldn't find one that would work with IPv6 and just had the 00 like he has in the book in this thing. So let's go to interface serial 0/0/0, and then what's going to be my command here? IPv6 OSPF, I think, and then the process number, area, AREA, area 0. And then I should go to interface serial 0/0/1, because I put a space in it. Can't spell either. 0. Can't see and can't spell. And then, so I have to type all that stuff again. I can use the up arrow key because I'm reusing the command IPv6 OSPF area. And see if it's working. Yeah, good. There it is showing. So we have neighbors. We should be able to go in here and show IPv6 IPv6 route OSPF show IPv6 route. Guess I typed it wrong the first time, but there are, the O's mean that it's OSPF, so it did do it, and that's just the process. One of the last labs you do in this chapter is an OSPF configuration. So, questions?